So far in electrochemistry, we have looked at standard electrode potentials, potentials of electrochemical cells or cell potentials, and the relationship between these cell potentials and the Gibbs free energy of the reaction, and the equilibrium constant or the reaction coefficient, which is related to the activities of individual ions. We have not, however, looked at the speed by which different ions approach their respective electrodes. So what we want to study in this part is to look at the net transport of ions or net transport of different charged species in solutions. And the number that is typically used to quantify this is called conductivity. So for this treatment, we need to segregate between different types of electrolytes. Some are strong electrolytes which ionize significantly in water, and this could be a solution of sodium chloride, hydrogen chloride, or similar salts. And they will have a lot of ions in solution. Or you can have weak electrolytes which form fewer ions in solution, and this could be ammonia in water or acetic acid in water, and so on. So different theories apply to these different types of electrolytes. We now define something called conductivity. But before that, we need to define what is called an electrical conductance. So we know that the resistance is equal to the potential divided by the current, and the electrical conductance, which is often called G, is equal to 1 by resistance. It was empirically observed that this electrical conductance, for which the units are mho, the opposite of ohm, they're also called Siemens for some historical reason that I'm not familiar with. It was found that this electrical conductance is proportional to 1 by the length of the conductor and is also proportional to the area of the conductor. So you could write this electrical conductance as some value kappa multiplied by A and divided by L. This is a proportionality constant, assuming this relationship is linear. This kappa is called the conductivity. However, this conductivity depends on the concentration of the charged species. So a more accurate description of the conductivity would be something called molar conductivity, which would be an intensive thermodynamic variable. And this is the conductivity divided by the concentration of the ionic species. The units of kappa are Siemens per centimeter or Siemens per meter. Typically this value is used. These units are used. This is because area is in meter squared, length is in meter, and kappa conductivity is in Siemens. All right. So if you empirically plot the molar conductivity versus the concentration, and here by concentration we are referring to the concentration of ions in solution or concentration of the electrolyte. Then for strong electrolytes which ionize a lot in solution, it is empirically observed that this follows a straight line and that the molar conductivity decreases with concentration. The same is true for weak electrolytes, but the relationship is a bit different. So as concentration increases, the molar conductivity decreases, and this is mainly due to interference effects in the case of strong electrolytes. So when the concentration of the electrolyte increases, you have more ions in solution, and these ions interfere with each other when they are moving to their respective electrodes. As the concentration of the electrolyte becomes weaker, there are fewer ions in solution, and therefore there is fewer interference of ions with each other, and therefore the conductivity or the speed at which the ions move towards their respective electrode increases. For strong electrolytes, there are two reasons for the decrease in conductivity. As the concentration increases, one is called the asymmetry effect. So we know very well that each ion in solution is surrounded by a cloud of oppositely charged ions. In this case, a cation is surrounded by anions. If we put this in between two charged walls, the cation will start moving towards the cathode and the ionic cloud will start moving towards the anode. And after some time, this is what the cloud will look like, which means that there is an asymmetric ionic distribution, ion cloud distribution around this central ion. And this cloud will then retard the ion because there is a larger negatively charged cloud around the ion than away from the ion. This is one reason. A second reason is electrophoresis. So in solution, these ions interact with solvent by means of ion dipole interactions. So when a cation is moving towards the cathode, it is also carrying solvent ions with it, along with it. But the ionic cloud is moving in the opposite direction and it carries a larger amount of solvent with it, which means that this ion encounters more solvent molecules moving against it and therefore is retarded. And this is an electrophoretic effect. So this is why the conductivity of strong electrolyte decreases as you increase the concentration. In the case of weak electrolytes, the treatment is a bit different, and this is typically handled by Arrhenius' theory, and we will not go into the details of weak electrolytes. And the basic idea is as the concentration increases, so if you have an electrolyte such as AB, it will dissociate in water to a limited extent. This is a weak electrolyte to form the ions A minus and B plus. At low concentrations, the equilibrium lies towards the right. So you have a lot of ions in solution. At higher concentration, the equilibrium moves towards the left. So the Arrhenius theory is used to explain why conductivity decreases for weak electrolytes. But we will not go there in detail because the laboratory that you are dealing with deals with strong electrolytes. Now, at least for strong electrolytes, you can see that you can obtain the conductivity at infinite dilution or at very low concentrations by simply extrapolating the plot. So if you could measure the conductivity at different concentrations, you could extrapolate this and obtain the conductivity at infinite dilution. But this cannot be done for weak electrolytes. After doing many experiments, a scientist called Kohl-Rausch determined different values of the molar conductivity for different electrolytes and different ions. And he came up with some generalities. The first thing he noticed is that ions in strong electrolytes independently migrate. And this is a very important assumption for your laboratory. So he noticed that if you took a sodium salt of sodium chloride or sodium fluoride or sodium sulfate or something like this, he noticed that the conductivity or at infinite dilution for sodium remained the same. Therefore, each ion makes its own contribution to the molar conductivity. So the total conductivity of the electrolyte is given by the conductivity of the cation plus the molar conductivity of the anion. In order to calculate these, one needs at least one of these two values and the overall conductivity. Now it turns out that the individual conductivities of ions are proportional to their speeds. And this is quite obvious. The faster the ion moves, the more it will conduct, the faster it will reach the electrode. And it can be shown that the fraction of charge carried by a certain ion, so let's say the fraction of charge carried by the cation, which is equal to the total current carried by the cation divided by the total current, is equal to the velocity of the cation divided by the sum of the velocities of the cation and the anion. In some cases, these are also called mobilities. And these mobilities or velocities are different and depend on various factors such as the diffusion coefficient, the viscosity, the size of the ion, and so on. Or in other words, the ratios between T plus and T minus will be equal to the ratios between the ionic speeds. This T plus and T minus, these are called transference numbers. And you will run an exercise in the lab where you will use something called the Hittorf's method to calculate these transference numbers. More details about the method will be provided in the laboratory manual.